Welcome. We have been looking at some mathematical concepts. We looked at what is a group, what is symmetry, what is point group symmetry, how to define symmetry for a physical property, and how the point group symmetry of a crystal is related to the symmetry of the physical properties of that crystal. So, that is one mathematical idea that we would need to understand phase field models. The other important mathematical idea is related to functionals and their minimization. So, in this lecture we will try to understand what is a functional and how does one understand minimization of functionals. To start with, we will start with the Taylor series expansion, and for a function which looks something like this. Okay. So, let us consider some f of x and it looks something like this. Okay. So, f of x looks something like. So, if you have a function like this and if we wanted to know where the maxima and minima of this function are, then the conditions for such maxima and minima, there are necessary conditions, there are sufficiency conditions, and they can be obtained by looking at the Taylor series expansion. Let us say that I am looking at a point A, which is an extremum point. Okay. So, let me say that this is an extremum point. So, this is f of A, this is A, and so I do a Taylor series expansion about, so A, I consider a point x. So, and so that is nothing but f of A plus f prime, that is x minus A multiplying f prime of x evaluated at x equal to A plus x minus A whole squared divided by 2 factorial f double prime of x evaluated at x equal to A plus and so on, and where f prime of x is nothing but d by dx of f. So, by looking at this, we can find out what is the necessary condition, for example, for an extremum. To do that, let us rewrite this part a little bit differently. So, f of x minus f of A, right, I have taken f of A onto this side, is nothing but x minus A times f prime of x at x equal to A plus x minus A whole squared by 2 factorial f double prime of x at x equal to A plus so on and so forth. Now, if you look at this f x minus f A, if suppose I am at a maxima point, then we see that if I choose x to the left of A or to the right of A, in both cases f of A is going to be larger than f x of A. So, f x minus f A has to be, so these are the x points. So, f x minus f A has to be a negative quantity, right. So, we know from the geometry, for example, from the curve, for example, how it looks. So, if you are at a maxima point, so any nearby point you go and evaluate the value of the function. If you take the difference of the function at a nearby point minus the maxima point, that has to be negative, that has to be less than 0, right. So, we have this condition. So, f of x minus f of A should be less than 0, that should be negative, but this quantity is nothing but this x minus A f prime of x evaluated at x equal to A plus x minus A whole squared by 2 factorial f double prime of x at x equal to A plus so on. Now, if this quantity has to be negative, and this has to be negative irrespective of whether the x that I choose. So I am at a maxima point, this is my A, sometimes I might choose an x here, sometimes I might choose an x here. When I choose to the left and when I choose to the right, then the x minus A is going to have opposite signs. If I have chosen x here, then this x minus A is going to be negative, but if I have chosen x here, this x minus A is going to be positive. So, this quantity will become positive or negative depending on where I choose x, but this quantity has to be necessarily less than 0, which means the only way that condition is satisfied is if f prime of x at x equal to A itself is equal to 0. Okay. Now, because this has to be negative and because x minus A whole squared, irrespective of whether you choose x to the left of A or right of A, that is going to be a positive quantity. 2 factorial is nothing but 2, so that is a positive quantity. So, this entire coefficient here is positive quantity, which automatically implies that f double prime of x evaluated at x equal to A should be less than 0. If that is more than 0, then this would not be satisfied. So, if you can pick an x which is quite close to A in such a way that all the higher order terms can be neglected, then the Taylor series expansion tells that it is essential that f prime of x is 0 and f double prime of x is less than 0 for this function to be having a maxima at A. By the same argument, using a similar argument, if suppose I say that A is not a maxima point, but a minima point, a point that looks like that, and this is my A, then also you can look at f of x minus f of A, right. So, if I am at a minima, either way I go, f of x minus f of A has to be greater than 0. If that is so, then I have x minus A f prime of x at x equal to A plus x minus A whole squared by 2 factorial f double prime of x evaluated at x equal to A plus and so on and so forth. Now, again, if I choose x to the left of A or to the right of A, this is going to change a sign, but we want this quantity to be positive. So, this means that f prime of x evaluated at x equal to A should necessarily be equal to 0. That is 0, and because this coefficient is always positive, the sign of f of x minus f of A is determined by f double prime of x, provided you choose x small enough that higher order terms can be neglected, in which case f double prime of x should be greater than 0 for this to be a minima. So, these are conditions that you can derive from a simple Taylor series expansion. There is one more notion that is the local extrema. So, we consider a function, for example, f of x as a function of x. So, you have something like that, for example, right. So, when we are looking at these x's about the minima point, so there is an admissible value of x, okay. There is an admissible x, okay. So, for example, if I am trying to see if this is a minima or maxima, I cannot do it because I mean it can so happen that this function goes and then goes somewhere below and then comes, right. So, I cannot compare the f of x at this A value with an x which is very far away. I mean that I should look in the vicinity. This is also important because I am Taylor expanding and I am going to throw away higher order terms. So, I should be as close to x as possible. In the admissible values, assuming that I already have an extrema at f of A, because that is what helped us decide whether f of x minus f of A should be greater than 0 or less than 0, because I assumed that it is an extrema, depending on then whether it is a minima or maxima. In any case, irrespective of whether it is minima or maxima, we find that this quantity, the first derivative has to be 0, and the second derivative sign actually decides whether it is a minima or maxima. So, these are local extrema, and if you can find all the extrema for a given function, and whichever is the lowest is known as the global extrema. In this case, this is the global minima, maybe this is the global maxima, rest of them are all maximas and minimas. So this is as far as a function is concerned. So we have what is a function? There is a independent variable x, and for every value of that x you have f of x, and we have also assumed that we defined the Taylor series expansion, which consisted of f prime of x and f double prime of x, which means that these derivatives exist, right. So f prime of x, f double prime of x, etc. exist. Right. If those derivatives do not exist, you can't write that Taylor series expansion. So Taylor series expansion actually helps us understand where the minima or maxima for a function is, and it is a single valued function. It just took a scalar x, and for that x it gave you what is the function value, and by looking at Taylor series expansion of this function about an extrema point, it could be a minima point or maxima point, and by looking at points quite close to that, so that higher order terms can be neglected, and then one can make comments, and this can be generalized. For example, it is possible that for some function f prime is 0, f double prime is 0, and then you look at f triple prime, and then what happens. So there is also this notion of saddle point. So these things are possible. Now what we are interested in is what is known as a functional. What is a functional? Functional is actually a function of a function. So what is this idea of a functional? And once we define what is a functional, then we would like to understand how to find out its extrema point. So that is what we want to do in this lecture. The easiest way to understand functional, for example, is to look at the quantity called action, which is defined in classical mechanics. So action is defined as some t minus v, where, so this classical mechanics, T is the kinetic energy and V is the potential energy. Now you can see that what is kinetic energy. Suppose if you consider a particle, the kinetic energy of the particle will be half m v squared, and potential energy is typically a function of position, right. For example, if you are considering in the gravitational potential, then depending on the height of this particle with respect to some reference, if it is h, then you will have the potential energy as mg h, for example. Okay. In general, potential energy can be thought of, so the potential energy is nothing but a function of position, and what is velocity? So it is half m x dot squared. So the so called action is nothing but half m x dot squared minus v of x. Okay. Now if you integrate this quantity over x, this action can also be written as, suppose you are integrating it some from position x1 to x2. So this can also be written as a functional of t, which is a time, x, which is a position, and dx by dt, which is what is noted as x dot and integrated over dx. So dx. This we now call as a functional. It is a functional because what we are saying is that the t is the independent variable. For every time there is a position, and even though there is a derivative, which is the derivative of position with respect to time, which is the velocity, we consider that as an independent variable. Why do we consider that as an independent variable? We consider that as an independent variable because, for example, I might be at this position at some time t, and so t and x are fixed, but my velocity at this point could be anything, that is a completely independent quantity. For example, I might be stationary point, in which case x dot is 0, I might be having a velocity to the left, which is say 10 meter per second, then v is 10 meter per second to the left, and I might have 10 meter per second to the right, I might have 2 meter per second at an angle which makes say 30 degrees with the x axis. So, everything is possible. So, we just because I have fixed my position and fixed my time does not mean that I have also fixed my velocity. Velocity becomes another independent variable. Because of which, if you look at this quantity, now it is a function of a function, right. The position itself is a function of time and the velocity is a function of the position. So, at different positions it might have different velocities, and so they all have to be. So, the independent variable is t, but x and x dot both have to be considered as dependent variables, but they are not fixed. By fixing x, I am not fixing x dot, even though for every t I can give you an x, but at that x point what is the velocity is still a independent variable. So, this is known as a functional. So, functional is a function of a function, and typically it has this form. Typically a functional is an integral from some point to some other point. In this case it is whatever from position. So I have made a mistake. So, if this t is going to be the this thing, so we have to integrate with respect to t, and this is dt, right. So, this is t1 to t2 and then dt. So, typically a functional has this form, integral some points to some point. So, that is a variable which is getting integrated, and then some f, and then that is that independent variable, and then the variable that depends on that variable, and another variable which is a derivative of this with respect to this, but considered as an independent variable. So, this is an example of a functional. There are several classic functionals that one comes across. For example, in the so called geodesic problem, we come across a functional, and that is as follows. Suppose I have a point x1 comma y1, and I have another point x2 comma y2. What is the shortest line joining these two on a plane like this? We know that it is a straight line, but if suppose I am looking at a globe kind of spherical surface, for example, right. Now, if I want to find out 2 points x1 y1 and x2 y2, what is the arc which is joining these 2 points, which will have the smallest length. Arc, because I am on the surface, I mean you can think of it as a rubber ball, for example. If I take 2 points on the surface of a rubber ball, and if I want to find the what is the line that is joining them, which will have the shortest distance, then I have to go through this arc. It is no longer a straight line. So, this for example is written as a functional. F is equal to I is equal to x1 to x2, because I want to write the distance, that is the shortest distance I want. So, it is nothing but dx squared plus dy squared, and so integrated from x1 x2. So, that is nothing but x1 x2 square root of 1 plus y prime squared dx, right. So, now this in this case f is x comma y comma dy by dx, which is the slope. It so happens that this functional is an explicit function of only dy by dx, x and y do not appear, unlike the case of action functional where t did not appear, but both x and x dot appeared. Okay, but it is still in the same general form, just that this is not an explicitly x or y dependent functional, but it is a functional all the same. There is also this famous problem which is known as Brachistochrone problem, that is the shortest time problem, and the shortest time problem is defined as follows. Suppose I take 2 points and I connect them through a chute, right, and then I leave a particle here with some velocity v1 and under the gravitational field, and then it reaches this point, and I want to know what is the shape of this chute which will have the shortest time for this particle to traverse from this point to this point, right. So, we know that at every point it will have some velocity, let us say that velocity is ds by dt. So, I want to know the shortest time. So, dt is nothing but ds by v. So, the shortest time will be obtained by looking at this functional which goes from point 1 to point 2 ds by v, and that is nothing but point 1 to point 2 ds is nothing but square root of dx squared plus dy squared by v, and again you can use the same trick when it goes from point 1 to 2, 1 plus y prime squared square root dx by v, and energy conservation can be used to identify this instantaneous v and replace it. How does that work? So, you have this half m v1 squared, which is the initial velocity, minus whatever potential energy, suppose that is at some height h. So, you have m g h and is equal to, so let us call that as h1. So, let this be some h1 with respect to some reference, and this should be some h2. So, that will be equal to at suppose I am at some height h here, then half m v squared at that point will be equal to m g h. So, you can cancel all m and you can get an expression for v which is nothing but, so all m goes away and you have 2 multiplied. So, it will be v 1 squared minus 2 g h 1, and this minus will go there. So, it will become plus h. So, minus h, minus into minus will become plus, that is. So, you can come and replace this v here, and that gives the functional for the so called Brachistochrone problem. Okay. So, if you write the functional for the Brachistochrone problem, substituting all that, you get this functional. So, what is the functional now? It is equal to integral 1 to 2. So, you are integrating in dx. So, it is x1 to x2 if you want to put it that way, square root of 1 plus y prime squared by square root of v 1 squared minus 2 g h 1 minus h dx, right. So, if you integrate like that, and the h 1 h are basically the x's, you are going in the height, then you minimize this function, you will find the shortest time. So, the solution of this will give me shape of the chute for a particle which is left with velocity v 1 on top at h 1 position to come to h 2 at the shortest possible time. So, this is known as a Brachistochrone problem, and there is some interesting story about this problem told that how this problem came to be, which you can look up and find out. Our interest is in trying to find out, like we said, suppose if I have a function, I know what is the necessary and sufficiency condition for that function to have an extremum, which is a minimum or a maximum at any given point. Can we have a similar concept which tells me, for example, what is the necessary condition for a functional to have a minimum, because all, as you have noticed, all functional problems have been posed as an minimization problem or maximization problem. We noticed that a geodesic problem is the problem of finding the shortest path, and Brachistochrone problem is a problem of finding the shortest time required for traversing some distance, and action is also defined in classical mechanics, and there is a principle of least action. Okay. So, the action, which is the functional that we wrote, should be minimized. So, this is what in classical mechanics one comes across. So, we will see a similar thing, we will see it in a thermodynamic setting. We will write free energy and we will demand that free energy should be optimized. So, being a free energy, it has to be minimized, and we will see that the free energy that we write is actually a functional, not a function, and that is where this necessary condition for a functional to achieve minimum or maximum becomes very important. So, which is what I want to do in the next part of this lecture. How do we find out what is the optimum or minimum or maximum for a given functional? How do we get this condition? In the case of simple function, it is just that the first derivative should be 0 at that point where extremum is achieved. How does it work in the case of a functional? We will look at it in the second part of this lecture. Thank you.